Hello, my name is Pierre Gibault, and today I'm happy to be presenting my project on facial recognition. Before we jump into facial recognition, I want to open up with just the idea of biometrics. Biometrics are unique physical and behavioral characteristics, and so those are different things that we can use as measurements. So in that case, it could be fingerprints, it could be our faces, it could be our eyes, or it could even be our veins. And so the idea is that we can use any of these unique characteristics to actually identify an individual. So one of those ways is that we can use facial recognition. So facial recognition works by just looking at your face. It could be either in a 2D format, such as with an image, or it could even be using a 3D image or 3D file, such as Face ID by Apple. So as you can kind of see on the right. But what's really neat about facial recognition is that it's, like a lot of these other biometrics, it has incredibly high precision. So if we were to compare facial recognition against, for example, a single finger fingerprint, you can see that it is higher. There's a higher accuracy. Now, you could also use vein scanning or iris scanning, and those are said to be more accurate. But the reason I really wanted to kind of compare facial recognition and fingerprint recognition is that in kind of society today, those are the two most common ones that we kind of use in our day-to-day life. So whether it's for opening a laptop, a smartphone, those are definitely more common than iris scanning or vein scanning. But yeah, so something that's actually really neat about facial recognition is that it's actually much cheaper than a fingerprint. And so it's something that I never truly thought of, but if you think about it, when a device has a fingerprint reader, that's an extra component. So you need the fingerprint scanner, which is usually costs a lot, and then after that you need all the software. What's neat about the facial recognition is that you actually only need a camera, and so a lot of kind of budget phones and laptops, they're much happier about being able to use facial recognition because they're already going to have a webcam or front-facing camera anyway. So it allows them to make all their products cheaper while still having that kind of premium security. And then another thing is that facial recognition is actually easier to obtain. So it's easier to just get a picture of someone and then crop it rather than trying to get a fingerprint. What can happen a lot with fingerprint is that you get partial prints, or there's just a lot of dirt on a finger, or it just becomes very hard. On top of that, when you do a fingerprint, each finger has a different print. So you pretty much, to be able to identify someone using a fingerprint, you need to make sure that you're always kind of using the same one. So it just facial recognition, just especially in our day and age, seems to be able to kind of have more usability in our day-to-day lives. So there's multiple ways that facial recognition can be used or done. And so the simplest one is actually using what's called the k-nearest neighbor algorithm. And this is kind of considered one of the simplest algorithms in just machine learning. And that's because in a sense it actually doesn't do any learning. All it does is that it compares an image, for example, to other images, and it tries to figure out what it's closest to. So while it's really nice because it's really simple, it is also very computationally expensive because you have to compare that one data point or data set to every single other data set that you have. And so because of that, you also end up using a lot of memory. Another kind of algorithm that can be used a lot for facial recognition is support vector machines. And these are much better suited for the KNN algorithm because they're very good for high-dimensional spaces. And so that means that you can actually much more easily compare kind have two images and actually have a multitude of features. So the way that a support vector machine works is that it pretty much creates a hyperplane. So that is n minus 1. That is like the dimension of n minus 1 actual features. So that's why in the graph on the right, we have, it looks like a line, but it's technically a plane because there's only 2 dimensions. However, we can bring that to maybe 3 dimensions. So on top of ear geometry and snout length, we could have fur color. And then you can keep adding these different features or dimensions, and then you can end up creating a hyperplane that divides it. The downside to support vector machines is that when you have a really large training set, it requires a really long time to train. On top of that, it just requires a lot of memory, and that's because the way that it stores things, you actually are, the memory is being multiplied quadratically. So you end up just having a lot of memory. On top of that, the data generally, the algorithm only usually performs well when there's a clear margin. So if we were to have kind of at least again in the example on the right, a cat that kind of looks like a dog and it's kind of were to be somewhere along that line, the algorithm would have a really hard time being able to determine which one it's supposed to be. And the last thing is that support vector machines are incredibly hyperparameter dependent. In a sense, most machine learning algorithms are, but this one, it just requires a lot of testing to make sure that you have the right hyperparameters. So in the previous slide, pretty much we were showing what would happen. We were showing like if this is either this or that. And so that's something that we can kind of struggle with support vector machines, is that at heart they're what's called a binary, they have a binary output, so it's either a this or that. And so in our case, when we do facial recognition, there's some instances where we might want to do what's called a multi-class support vector machine, because we don't want to necessarily say, oh, is it this person or not, but we want more like, out of this group, which person is it? And so when that happens, we have pretty much 2 options. So one of them is called the 1 vs 1 technique. And so this is essentially doing a support vector machine, as we talked in the previous slide, but doing it for every single combination in the group. And so this is just very, very, very computationally expensive, because you have to kind of train the data for 2 groups, compare them, and then do that for the rest of the data set. So it takes a long time because you're essentially just comparing 2 things at a time. Now, the other option is doing what's called the 1 versus all technique. And so this is different because it pretty much, as you can see, for example, if we look at the red data, it'll try to make a plane or a hyperplane that separates the red data from the rest of the data. Now, while at first glance this might seem really good, it actually will kind of create an unbalanced data set. And so what pretty much means is that if you, assuming that we have a group of 10 individuals, and they all have 10 pictures each, we will have one data set with 90, the one data set will have 10 pictures, and then the other one will have 90. And so in that case, even if we had a 0 classifier, which is always going to go for the bigger side, we would have 90% accuracy. And so while that may seem really good, at the end of the day, we actually can't really base any kind of good performance off of that. So 1 versus all is generally not recommended. And so in that case, the real kind of option is to do something that just takes just a lot of computing power. So the last kind of option that we're going to be exploring today is the convolutional neural network. And what's great about this is that it's really meant for image classification. And what it does is CNN is inspired by how human thinks. by how humans think, and so it detects important features in an image, and then pretty much can take that feature and then just kind of bring it down until it gets to a neural network. So what's really nice about this is it can handle a very large data set, and ideally you actually want a really big data set because it allows you to, it pretty much makes sure that your neural network doesn't end up overfitting your training data. And then even though we usually associate large data sets with kind of memory issues or with performance issues, because of the way that this is coded, it generally can actually do multiple processes at once, and so it can help it go faster. Yeah, overall, because of the way that convolutional neural networks work, they end up being more accurate. So compared to the previous two that maybe had 70% accuracy, these are usually a lot of tests with using CNNs will have about 95% accuracy minimum. The only downside to convolutional neural networks is that because you do have so much such large data sets and so much is happening, it can require faster hardware like a graphics card. And otherwise it can be pretty slow.